Hello, everyone, and welcome back to Creation Myths. This video is, I think, a really interesting conversation, what I'm about to show you here. This is a continuation of the conversation that I've been having over the course of, at this point, a couple of months with Rebecca from Bread of Life and Examining Origins on nested hierarchies and the evidence for common ancestry versus common design, as you hear from creationists. So this conversation, if you kind of think of the backstory here, I did my little like simulation video thing. And Rebecca and I had a conversation on that where I did it live for her on her channel, Examining Origins. And it left her with some stuff to think about. She thought about it some more and had additional questions. So she was doing one of her kind of call-in show live streams, and people on the show were talking about it, and I happened to be available and was watching, so I jumped in, and I spent a little over an hour just talking about it, talking through the questions and kind of why I designed it the way I did, and how what I did differs from, the real papers on this, because my little simulation is like an oversimplification. It's just a simple illustration. It's not meant to be like real data. It's just to illustrate kind of a simplified version of how this stuff works. So this conversation was me, Rebecca, Grayson, friend of the channel, Grayson from Grayson Hawk was there, and he was really helpful clarifying a few things. I'm going to link his channel down below, so you should check that out. And then a quick note here, there are a couple points where I cut out parts of the conversation because also in this stream was Pigs Can Fly, who is a creationist, and honestly, he's kind of annoying, and he has like a very specific script and playbook that he follows, and he kept trying to bring it back to like the thing that he wanted to talk about, which is not what we were talking about, which is Winston Ewert's dependency graph model, which is off topic for what the rest of us were trying to talk about. So there are a few places you'll see, and I put a little note in there, where I just cut out like a few minutes at a time because it's just an off-topic digression and it doesn't matter. But rest assured, I will have more. I've been working on stuff related to Winston Ewert's dependency graph model, and I'm going to have stuff on that separately in the future, so don't worry. If you want that, it's coming. But it's not relevant for this conversation, and it disrupted the flow while we were doing it. So I cut those bits out, and it's noted in the video that you'll see where that happens. But other than that, I thought this was a really enjoyable conversation, and I'm always happy to talk to creationists and address questions they have about stuff that I say, papers, whatever, right? I'm happy to do that. I actually have extend that invitation to Pigs Can Fly because he's expressed concerns with my model, and I've said email me and we'll set up a time. And to date, as I record this, he has not yet done so, but maybe that'll happen in the future, and I would love for that to happen. So enjoy this conversation, everybody. It's a little bit over an hour long, and I think it's really interesting kind of how it ebbs and flows. And once again, in particular, I want to shout out Grayson from Grayson Hawk, because he helps kind of clarify some of my explanations, as you'll see, in really excellent ways. I think his contribution to this conversation is really, really important. So Grayson, thank you. I appreciate you. With that all said, enjoy this conversation, everybody, and I'll see you on the other end.
Yeah, hey, Rebecca, long time no see.
Yeah.
As long as we're going over evidence for evolution, I do think that the patterns of genetic similarity by it of themselves are sufficient, even if we didn't have any fossil record. But specifically, I would point to the congruence between the fossil record and the patterns we see in, nested patterns of genetic similarities. Specifically, I also think that your conversation last week with Dr. Dan, I thought that he presented some pretty foolproof evidence for evolution in the patterns of genetic similarity that we see that don't seem to be able to be produced by any model that involves the created kinds, right? I mean, he was showing that the patterns that we see when looking at the genetic variability in different organisms, not just on the gene level, but in like the non-coding DNAs and the patterns of their actual mutations. Those patterns are not replicable with a created kinds model. If the pattern of created nested hierarchy that we see was created at the start in these kinds that are, phylogenetically an orchard instead of going back to a single root, then the patterns of mutation that we see are incongruent with that model, as in it rules it out based on the scientific evidence.
Well, I
Right,
haven't been
for sure.
shown that yet. Actually, I know that you think Dr. Dan presented good evidence for that, and maybe Dr. Dan does have something that he can show me. So I actually sent a private message to Dr. Dan to ask him to clarify and actually demonstrate what he's talking about, because and I pointed out the flaw with what I thought was the flaw in the demonstration that he did. Okay, so and he's here and he thanks you for talking about bringing up what he brought up.
Nice.
So I'm not ruling that out yet, but for me right now, I have not seen and the main problem that I'm having with this is that you guys are assuming that if something doesn't have a common history, I mean, if that it would have no genes in common. So
right. So this is not on the gene level. I want to clarify.
Okay.
Like, we're specifically talking about like mutations to the entire genome, not just between genes or whatever. But if we're looking at like the whole genome, and we're looking at, oh well, here's a mutation in this region, right? And you could see that certain species share certain mutations in the same region, and that either has to be a coincidence, or they're both inheriting those mutations in that specific location on the genome from a common ancestor. And so you can test those two models. And statistically, the odds of just all these patterns of mutations that we see in different organisms' genomes just coincidentally being the same mutations, if they don't share a common ancestor, is like less probable than you picking one specific atom in the entire universe. I mean, it's just statistically impossible.
Okay, I read the paper that said that. Okay, and it's very problematic. And Matt, I'll let you jump in just 1 second. Just let me say the last thing that I want to say about that, which is, Grayson, everything that you're saying is on the assumption. See, if you have common ancestry, then you had to get everything through mutation, right? In some, or whatever, gene duplication, whatever, but you have to, all the changes that you're seeing have to be mutations. But in my model, there can be differences that are not mutations, right? And not, and also not recombination. I mean, not recombination, like that were original to the organism. So you're assuming your assumed starting point is what's causing you to see these coincidental changes.
Right, but we both agree that mutations do happen, right?
Yes, absolutely.
Okay, so
But
then
see,
you have the issue of figuring out which differences are due to mutations and which differences are due to some sort of created design differences inherent to these kinds of organisms. And it seems like all of the differences that replicate that pattern of nested hierarchy, you then cannot label as mutations, because then you have to give up your position. But if it just seems kind of like a no true Scotsman fallacy, where if you find a difference, you rule it out as being a mutation because of your worldview assumptions.
Well, and let me steelman Grayson's position here, if I understand it right. I think part of what Grayson is saying is that when you lay out the genetics of an organism, for instance, and you're trying to say, like, in a kind of created kinds model versus an evolutionary model, what is the thing that's telling you of something, right? That if the similarities are occurring are the result of God choosing to do whatever he chose to do, versus mutation, right? And the problematic aspect of that is going to be, in certain organisms, you may see certain similarities, right, that make sense of, like, oh, well, of course, of course, cheetahs and, like, let's say, like, leopards have similar mutations and things that correspond to their eye because they both belong in the cat kind, right? But certain other things that you may not accept as being related to each other, like the eye of a cheetah and the eye of an octopus, even if they operate very similarly, right? You would say, oh, those mutations aren't necessarily like that. That's just what God chose to create, like separate creation, right? And it seems like the basis by which you're choosing to do that is arbitrary, right?
I'm not saying that I can scientifically determine that, right?
Well,
Right. I
And
think Matt
so,
wants to jump in. So let's let Matt respond to all of this, if that's okay.
Yeah, I just wanted to speak a little bit to what Grayson said, and I mean, he had a very thoughtful response. I appreciate it. But I just wanted to say that. So, I don't know if you saw the video with Dr. James Tour and Rob Stadler when they went over that information, and Rob Stadler actually laid out a very thorough refutation of what was taking place there, and explained about how they had many assumptions from the start of the paper that are already in depth explained in the paper, but you kind of had to go do some digging to verify it, and it obviously already assumes a certain model of creation before they ever try to, attack it, of course. And then it gives them that p-value that was extremely, high that you were talking about, where it's like, you couldn't even select one atom in the entire universe, especially compared to this other thing. I understand that's a pretty crazy p-value. That's insane, right? But that's assuming that it wasn't using something like the dependency graph model. That's what Rob Stetter had brought up, which actually apparently was highly favored over the tree of life model, right? So if you had gone and verified that, you would see what was going on. And I'm not sure if you had actually got to hear that or not, but so the dependency graph model actually is similar to like what software engineers use. Essentially, they will go and they will take these dependency graphs where they have multiple sets of code, and to perform a specific task, that code is already preset. It already has like a certain base, code set, right? And so the programmers will come in there, they'll take a portion of that, whatever is required for their job, and then they will modify it according to what they're trying to implement it in for that particular job that they're doing, right? And so those different things might get put back into the overall dependency graph, but you can see that that's where they were drawing from, was the original code, right? And it could be the same in that model when it comes to what God could have done there. Now, just to be clear, this doesn't prove creation or anything like that. I'm not saying that's the case, but just to be clear, it's just like, you can't rule it out. That's the biggest issue here. And it seems like it's all automatic a priori. They're assuming evolution without us at least giving the designer a chance to do what he's supposed to. And
So
that's what
I
every
want
designer today is doing, just to be clear. So it's like, why would we assume that the designer would do anything different, if not better, than what we're doing right now, right? You see what I'm saying?
Yeah, so I've read the paper. I've seen Dr. Dan's simulation that he did that was similar to the idea in the paper, but I haven't seen Stadler's response. But from what
Okay.
you just conveyed about it, it doesn't sound like it's accurate because, I mean, the paper did not just assume evolution, neither did Dan's model. I mean, they're testing two different models, one of which is the created kinds model that doesn't assume evolution, right? What it assumes is that God created the nested hierarchy pattern that we see today in genetics in that same nested hierarchy at creation. And you had these separate created kinds that were fitting into a genetic pattern of nested hierarchies. And then the only thing that goes from there is that the species mutate. And all of us agree that species mutate. So we're just saying if you have a starting point that is the creationist starting point, or however you want to do separate created kinds, you can literally input it yourself into Dr. Dan's model and see what the results you get. As long as you have mutations, that's all that is required to rule out creationism. I'll look at Stadler's video or response
Yeah,
to it. Maybe I'll
I
make
would
a response.
recommend. I'm sorry, not trying to cut you off. I just want to say I would recommend just taking time to listen to what he actually said, because I don't know if I represented it properly, but what I was pointing out is not that they're assuming evolution to start. What's happening is they are mischaracterization. They have a mischaracterization of what the creationist model is. They're not presenting the most accurate representation of how a designer would do something. They are
I
assuming
mean,
specific ways, and then they're strawmanning that position and saying that therefore that can't be true, and then they're applying it to every single design model that could possibly exist. You see what I'm saying? That's the issue. So that's
I
why I would say, look, I understand you can have your model, and in some sense it could work, but I also want to contend with what Dr. Dan has not done so far. He has not been presenting any models that actually take into account mutator genome decay, right? And that's a huge issue because even the NIH is recognizing that. So it's been in their literature for over 10 years now. They've been talking about it all over the place, but people don't bring it up because it's a pretty detrimental thing to the evolutionary theory. Ultimately, what's taking place there is they have shown how every single genome, if it's not identical to its parent genome, ultimately has a net loss of genetic information per generation, right? And if that's the case, then that actually throws a huge monkey wrench into your whole theory. Now, they don't talk about that, and obviously you can see it's not his models, right? You're not seeing the genetic mutation with decay over time. You're actually seeing the assumption that there's some kind of producing of new genetic information that's going to be functional in the future. And that's an issue. I'm not saying that there can't be functional information. The issue is that we're always assuming it without taking into account the issues with that, right? I want to say that that's what's going on here.
Oh, well, it looks like we have the author of the
The
paper.
big dog's coming in. The big dog's
Hey, the man himself. The man, the myth, the legend.
Chat, and I had to jump in because I couldn't type fast enough to say all the things that I needed to say in response to what I'm hearing. So how is everybody doing?
Good.
I'm great. That's fun.
Okay, so can I just say real fast, two things from the last like 5 minutes of this that I was explaining in chat, but like I said, I can't go fast enough to keep up with the conversation live. So first, that paper, Rebecca, the paper that we're talking about, the simulation with the super low p-values.
Yeah.
They didn't pick a starting state. There was no assumptions about starting state at all. And if you dive into the methods of that paper, what they did is they said we have several different models that we're evaluating, right? There was species, separate ancestry, family, separate ancestry, and then universal common ancestry were the big ones. And what they did is they said, okay, we have what exists. We can directly document that. Given the processes, what's the likelihood? And they used two different models. There was a parsimony and a likelihood, and those have like very specific definitions, but it basically is what it sounds like. Parsimony is fewest changes, and then likelihood takes into account things like the asymmetrical mutation rates, that kind of thing. Like C to T is more likely than T to C. And so they said, given what we directly observe in terms of existing genome sequences and patterns of similarity, and what we know about how genomes change, then what is the likelihood and what are the most parsimonious processes or parsimonious histories that get us from origin to current state? And what they found was that common ancestry is very parsimonious, highly likely. Family and species, separate ancestry, non-parsimonious, highly unlikely, right? And again, there's no assumption about the starting state because the way those models work is they're iterative. So you keep trying different variants of like, oh, the computer generates a lot of variation. And then it's almost like a natural selection kind of process where you generate a bunch of phylogenetic trees and kind of pick the best ones according to each model. And then each one will converge upon the best trees. So there was no assumptions built into that about the starting state. So I want to be clear about that.
I don't see how you can not build an assumption into the starting state, though.
The way you do that is I say this not in any malicious way, but it like, if you're not doing graduate level phylogenetics, you wouldn't necessarily see that because you're not looking under the hood of how these different things work. But if you look at how the different ways of doing phylogenetics work, there's different methods of doing it. And the way they did it is looking at existing diversity and working backwards while being agnostic about what that initial state was.
Okay.
So, Dr. Din, I have a question.
And then second thing that I was trying to type really fast was to Pigs Can Fly, talking about how I did not take into account things like genetic decay in my thing. I didn't have audio for just a couple seconds while I was joining StreamYard because it was muddled and overlapping. But Pigs Can Fly, is that a fair representation that I'm not considering like genetic decay in my simulations?
That's correct. Yeah. So there's, as I mentioned before, the NIH has already spoken about this over a decade now.
Are you familiar with the paper that I co-authored last year with Dr. Zach Hancock?
No, actually, I'm not. If you want to send it to me, I can take a look at it.
We refuted genetic entropy, which is all the genetic decay stuff is genetic entropy. That's what it is. And we mathematically refuted that using empirical distributions of fitness effects, which is to say, using experimentally determined distributions of the fitness effects of mutations as they occur. We showed mathematically that genetic entropy is wrong, Like that was a paper that was published in the Journal of Mathematical Biology last year. Dr. Zach Hancock was the primary author. I was the second author. If any creationist, you or anybody else, wants to say that genetic decay is a thing, it's a problem, it precludes evolution, whatever, you need to refute the math in that paper.
Okay, I'll certainly take a look at it if you wouldn't mind sending it to me. But I just want to clarify. So you're telling me that the NIH got it wrong whenever they were publishing that information over a decade ago, and they've still been talking about it, by the way, all the way up to this point.
Link the source, the NIH source, in the private chat so I can look at it. I think I know what it is.
I mean, you can simply type. You can literally go to Google Scholar,
link me, dude. Don't play
type
that game.
in mutator genome decay, and you will start seeing.
For the love of God, why don't you stick by your source and just link it?
I can't read your mind. If you want me to tell you if I agree with the source or not, tell me what the source is.
I just told you it was the NIH multiple times.
No, that's not good enough. I need title and authors.
To be fair, like you just asked
on a daily basis.
No, I can't just leave and then come back. It will give me a hard time about that.
That's what I'm pointing out.
You just demanded that Dan send you a link.
If you want me to tell you if I think your source is wrong, tell me who your source is. Give me a title and the authors, and I can look it up. But if you
know what? We can do that on another stream too. If it's not something that Matt can get right now, then we can get it later.
I linked our paper in the private chat, so everybody has access to it if you want to look it up.
Yeah, I'll definitely
and I can put that. I will put that in. Do you want me to put it in the public or no?
Absolutely, put it in the public chat. Absolutely,
okay.
It's out there. It's
I assume that Pigs Can Fly was probably referring to Dr. Sanford's talk that he gave at the NIH.
No, that's not the only thing. I mean, he, of course, is one of the people that's talked about it, but there's many people.
That's just genetic entropy, though. Then you go back to the paper.
It's labeled mutator genome decay by the NIH. It has nothing to do with
mutator genome decay. Stop right there. That's a Lenski thing, and the problem there is you are saying that because the mutator lineage has higher mortality, that it's showing decay, but that's wrong, because what happens is that the mutation rate goes up in the mutator lineage because they lose their DNA error correcting mechanisms. So they have a higher inherent mutation rate. What happens is the average fitness of that population goes down, but the maximum fitness goes up. And you get this dynamic where you're constantly finding the most fit genotypes, but then because you have a higher mutation rate, you're also mutating away from those most fit genotypes. And this means that the most common genotypes are not the peaks that have the highest fitness, they're the peaks that have the closest to 1 or 2 nucleotide difference fitness. So it's this whole dynamic called survival of the flattest rather than survival of the fittest. It refers to the shape of the curve. It's a flatter curve rather than a steep curve. And that's a well understood evolutionary dynamic under high mutation load. Important thing with that is that does not mean those populations are decaying or going extinct. It just means they have a different equilibrium point. And again, I'll emphasize the maximum fitness is going up, even as the average fitness is going down in those populations. So that's not an example of genome decay. What other creationist talking point would you like to throw at me while I'm here?
Wait, I want to go back. I don't want to miss this opportunity because I still want to go back to the separate ancestry in this paper. Okay, because I know you're telling me the reason I can't understand is because I don't do graduate level phylogenetics. Okay, but that's not going to suffice. Okay, like I can be made to understand what the mechanism is that you guys are choosing your.
Okay.
And you're saying, wait, hold on. You're saying it's agnostic. But to me, I don't see how you can be agnostic about your starting point. If you're calculating 4 separate ancestry, you have to be assuming something at the beginning. Now, what I could tell, you can correct me. From what I can tell about the paper, it looks like they're assuming separate ancestry by natural processes. So am I wrong about that?
The only assumption built into that paper is that the processes that occur from start to present are the processes that we observe today, and they're operating as we understand them today.
Okay, so do they do like, then I feel like you would need, if you were really going to do that scientifically, you would have to like have many starting points that you start with. Like, meaning like, okay, if we start with separate ancestry, we could start where they have these genes in common. So you did, okay, so how many different
what they do,
ancestry methods?
There is no single number for that, because the way these models work, the way they describe it in the paper, is they say, here's the existing variation and here are the processes. So given those two things that we're locking in place because we can directly observe them, right? We can sequence genomes and we can observe how mutations work, right? So we're going to lock that stuff in place, and we're going to be agnostic about all the other stuff, how it started, what it looked like when it started. We're not going to take a position on that. But for the different models, we're going to say for common ancestry, we're going to say all these things have to go back to a common ancestor. We don't know what that looks like, but given the starting state and the processes, how likely is it that that's possible in the, given our constraints about like mutation rates and the relative mutation rates and deletions and insert, right? Where all the processes we know. For family separate ancestry, they're taking this group and this group and this group and this group and saying, okay, each one of those has to go back to a starting place. And then that overall pattern that we see has to match the existing pattern that we directly document. And for species separate ancestry, they're doing the same thing, except they're starting with each individual species as it exists and saying, okay, given these processes, you have to get there, but you're starting from independently, right? You're starting in a different lineage and you have to work your way down. Now, what those independent starting points look like, the paper is agnostic about it, because you're working backwards from the present, and the models for each experimental run are going to converge on the best possible starting state for each of those models, right? So like the p-values for the separate ancestry model are the best possible p-values that you could possibly get, assuming like the optimal starting states for those models.
But okay, and I mean, I really hope you'll like just, if you, okay, I look, it is still assuming that those genes, common genes had to, or common genetics had to have a common history.
Nope. It explicitly.
I don't see how you're.
Says they
I feel
don't.
like we are either totally talking past each other, because like I'm hearing you say this, I'm understanding your explanation, but your explanation still is not addressing the problem.
It's just, let me try explaining it a different way. So what the three tests? So you've got common ancestry, family, and species, right? You've got your three options, and what each one of those kind of iterations of the model says is, what's the likelihood that if we start at the same point, we get the current level of diversity? What's the likelihood that if each species starts independently, we get the current level of diversity? What's the likelihood that if each species starts separately, we get the current level of diversity? And in order to answer that, we're saying, well, we know that mutations occur at this rate with this distribution of likelihood and blah, 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 right? And because, again, once you start, you're just operating with whatever observed processes we have, mutation, recombination, et cetera. So the model is not positing, and this is where it differs from mine, right? It doesn't say, here's what the starting state is. It doesn't do that. It just says, if we assume separate starting states, what's the most likely scenario that gets us to the current state?
And what do the starting states look like for each organism?
They don't. There's no other way for me to say it except to say there are no fixed starting states. There's no defined starting states in those models.
So you don't have anything to compare it to. If you don't have a starting state, you don't know what you should expect.
Can I try this
if
one?
If you want to try, go for it.
Yeah.
Okay. Like, so you have the common ancestry model. We got that one. The things that they're comparing it to are if each species did not share a common ancestor. So what does any possible starting state look like that gets you the results that we have today for each species if no species on Earth shared a common ancestor with any other species? And then they try another one with the family level as saying, what about if each family did not share a common ancestor with any other family? And they're not assuming anything about what the starting states look like. They're just saying, well, given all the different possibilities for what these starting states could look like if they did not share that ancestry, then what is the likelihood of us getting the results that we have today?
And how many starting state potentials did they calculate? What I saw was two.
I want to be clear about this. They didn't calculate starting state potentials. They didn't do that. The way these models work.
And I'm saying that's the problem.
Wait.
Okay.
No, the way these models work is it is an iterative process where the computer generates a certain number of outcomes, right? And then it evaluates the validity of those outcomes according to the parameters that it was given, which for this model are the relative mutation rates, the frequency of other genetic changes like duplications and such, and the existing pattern of similarity, right? Existing sequences, right? And what it does is it says, okay, we're generating all these potential pathways from A to B. How well does each of those match the parameters I've given? Are they highly likely or are they highly unlikely? And then what it does is it takes the most and you can do this for, there's different ways that some versions of this, you take like the 4 best out of 1,000. Some are a little more permissive and you take the top 10%, whatever it is, right? You take all your iterations and you say, okay, we tried this 1,000 times, right? Let's take the best 10% of those 1,000 trials. And we're going to start with those where we get the best match, right? The highest likelihood. And we're going to mess with those now by a certain level of change. And we're going to evaluate those 1,000 possibilities and take the best 10%. And we're going to then vary them again and take the best 10%. We're going to do that 1,000 times until we converge on a best answer to the question, right? That's how it works. So you're not telling the program, here's what the starting state is. You're letting it find the optimal starting state for each hypothesis.
Yeah, effectively what it's doing is like, I imagine like the number of possibilities that accumulate grows it grows exponentially. And basically what it's doing is it's saying, okay, based upon the certain set of constraints that the code is running against, right? Here's the best after a certain number of iterations. And from the best in iterating this process a certain number of times, what is the best what is the best possible thing you can get out of this, right? And in a way, I mean, it might even be overly generous because what you're doing is you're saying the best of these, right? The best of these stay, the rest of these you're no longer, right, worried about, some of these computations and back propagation, like with the program of computing, like what could have given rise to this. Right.
Okay. Now, let me tell you what I'm hearing that this experiment is capable of. It's capable of showing you whether common ancestry is a possible explanation. Okay. And it's showing that common ancestry is parsimonious with what we see in genetics at that level, right? So that may be what it's showing.
Well, it's showing that it's both parsimonious and high likelihood, which are two different
things. That's where I'm having the issue. And Dr. Dan, let me try to explain it in another way, because I thought about your demonstration. So maybe this will help you understand where I'm coming from. Let's suppose we did that demonstration again, where you did the separate ancestry versus the common ancestry. And you offered to me, hey, we can change the parameters if you want. Okay. Now,
Which I did.
I know you did. Now, but so let's suppose we're doing that again now, and we don't actually have to go through it I hope for you to understand the point that I'm having. What if the parameters that you used for common ancestry, we used that in the separate ancestry, like, what if I chose that as the parameters for the separate ancestry?
I'm not sure what you mean, because the parameters for common ancestry were just that they share common ancestry, which is the...
Okay,
right,
why do those parameters get to be the common ancestry why can't those parameters be the separate ancestry?
What do you mean when you say parameters? Do you mean starting points? Do you mean
The starting
changes
point.
after?
The starting point. I mean the starting point. The part
Here's
that
why.
you
Here's why. Because in the separate ancestry model, you're limited in the number of variation that pre-exists in each lineage. That's why.
But are you? That's what I'm
Yes.
challenging.
Yes.
Because you have a maximum
That's
of
what I'm
4
challenging.
alleles per locus. Yes. You are limited by the number of individuals that get off the arc. Yes.
But you're not limited. Now you're limited within one type
Kind.
of organism, a kind.
In a kind. Yes,
Okay, you're limited within a
yes,
kind.
Exactly.
Okay,
Yeah.
good. Matt's back. I'm not alone against
Let
30
me-
people.
let me-
No, hang on. Let's finish this point. You're limited within a kind. So keep
Okay.
going.
So, all right. So you're limited within a kind, but remember, your demonstration was not a comparison like of alleles within one kind. Your comparison was 3 different kinds.
Right.
Okay. So your comparison was 3 different kinds.
Right.
So why can't those different kinds have the same starting point that you used for common ancestry? This is what I'm trying to say. They may have common genes that don't share a common history.
Because you have to generate all of the within lineage variation after creation. That's the point. Is like there's like humans in the ABO blood group gene, we have over 1,000 variants of that gene. But at creation, there were 4 variants. So you have to generate all that variation. You know what I'm saying? So in the common ancestry model, some subset of that variation accumulates in the common ancestor. But in the separate ancestry model, all of that variation, the vast majority of which must be due to mutation, must accumulate in each lineage separately. That's why.
Yes, and like I said,
Rebecca, let me just ask a quick question. Do you disagree with that last sentence that I just said?
No.
Perfect. Then we're good.
Okay, but so I'm saying within a kind. So if you want to bring the blood group thing and do it where you actually account for mutation and recombination, and then it's still showing that we can't get those alleles, then I'll count that as a point for evolution. But the problem I'm having,
done that math. I've done that math.
No, I watched your video. I watched your.
Yeah, it's
I watched
off by
your video
30,000 times. It's off by 5 orders of magnitude.
No, I did. I watched your video, but you told me
that.
you didn't account for the mutations in that.
No, I did.
Okay, well then I'll rewatch it.
That's the point, is that in the creation model, you can't do it. You need to do it via recombination, because if you do it via mutation, the lineages diverge from each other and you lose the hierarchical pattern. So in the creation model, you must account for that variation almost entirely, not strictly, but over 90 some odd percent. Nathaniel Jeanson has the actual number, but I think it's like 98%. It has to be due to recombination. And that's not my number. That's Nathaniel Jeanson's number. Okay.
And I accept that. But remember,
that number requires that number requires the rate of recombination be 30,000 times faster than what we observe.
Okay, well, I have not looked into that, so I can't talk about that. And I will. Okay. And if what you're saying is true, I will grant the point against my young Earth position. It still won't be a point toward evolution, but it'll be a point against the young Earth position, right? Like I'm counting it as a point against mine. Now, but what I'm talking about with the demonstration, remember, we weren't going with one kind. We were going with 3 different kinds. So what I'm asking is, why can't my starting point be the same as your starting point when you said common ancestry? And this is the problem I'm having with.
I gave your starting point. Your starting point was a perfect nested hierarchy. Why would you want a different starting point?
Well, but I'm saying it's
the maximally generous starting point.
Well, I don't know that it's a maximally generous starting point. Okay,
because in the common ancestry, you didn't have a perfect nested hierarchy. You saw some variation in there. In the common design starting point in my model it was a perfect nested hierarchy where out of the 15 sites, 5 were shared by all 3, 5 were shared by 2 and then different in 1, and then 5 were different in all 3. That is a perfect nested hierarchy.
But
You can't get
I
better.
think you're
it
focusing a
assumes
bit
that we
too much on the
know the
hierarchies.
starting point. What's
Yeah, I was
that?
going to say that assumes that you know what we were starting with to begin with, Mr.
You can
Dan. I
pick
mean, I really
any
appreciate
look,
that.
you can pick any starting point you want. You're
Yeah,
not
but
going to get
that's why I'm
better than a
saying,
No,
nested hierarchy.
Dr. Dan, that's why
that's
I'm
not
saying,
true.
can I pick your starting point? Can I pick your starting point?
My
You took
starting
5.
point.
You took 5 that were that
Uh-huh.
you copied and pasted, right?
Right.
And you kept those and you generated variation
Because they shared common ancestry, right? Because they happened in the past when they were common
and
ancestors.
what
Yeah.
I'm saying is I would like to take that starting point and say they didn't share common ancestry, but they shared common genes. They didn't, those genes didn't have a common history,
right?
But the genetics shared commonality without sharing common history.
So how do you get the existing variation if they don't share common ancestry, right?
Right.
They were separately created with very few variants at creation. That is a necessity. We agree on that. How do you get the existing variation? How do you get the existing diversity?
Well, you didn't have to get them to get the existing diversity because they didn't start out together. We were doing human, chimp, gorilla. So they didn't need to get to any.
You want them to start randomly then with just random diversity in each lineage? Because I'll tell you,
I wanted them to start with your starting point. I wanted them to start with your starting point.
But my starting point was probabilistically determined based on a series of nested mutations.
But you're like, and that's what, but the whole point of this, Dr. Dan, is to show you why I'm having a problem with the calculations for separate ancestry. It's because you are assuming a starting point. You're still not admitting that, and neither is the paper, but it is that there is a starting point.
About this. We talked about this the other day, that when you say assume, you're saying as a basis for my hypothesis, this is the starting point, right? So in my model for separate ancestry, I assume they were created separately with the appearance of a nested hierarchical pattern. With the common ancestry, I assume they share a common ancestor and accumulate subsets of mutations in their common ancestors.
Yeah, just FYI, like if you went with Dr. Dan's starting point, you would be going with a shared common ancestor. So it would no longer be separate ancestry. But Dr. Dan's starting point for the separate creation model is the one that gives you the closest to the results that we see. Like if you used any other starting point, you could try it yourself. Input any possible other starting point, you're going to get a worse result.
It'll be worse. Dan. Yes. Thank you, Grayson. Yes, exactly.
But you guys are, that's the point I'm trying to make, is you guys are starting with something, right? So you're saying in this paper, they don't have they're agnostic at the starting point, but it's not agnostic at the starting point.
It is. It literally is. It literally is. There's no, like in my model, you can say, Dan, what sequences did you start with for run number 4 of your separate ancestry model? And I can say, here are the sequences we started with, right? I can.
But that just points out the assumptions that you made, Mr. Dan. That's the point.
Well, no, wait. I was making a very narrow point, and my point is this. In the paper, you cannot say what sequences did they start with. You can't, right? You can't do that. They didn't start with sequences and work forward. They started with existing diversity and work backwards. It's a different way of doing it. Now, my model is simplified, right? So I'm saying, let's start with a thing and work forwards. And you can say that there are assumptions built into my starting states, which is correct. There are, because we're hypothesis testing, right? So each hypothesis has assumptions that are inherent to that hypothesis, right? That's how hypotheses work. If you think that my model was wrong or uncharitable in some way, right? By saying, I'm going to start the separate ancestry model with a perfectly nested hierarchy and perturb it as mutations occur. If you think that is an uncharitable way to do it, suggest to me a better way to do it. Now, I can't just do the same thing I did for common ancestry, because then you're going to get, like, then it's a common ancestry model, right? Where the lineages share nested sets of mutations, right? That's common ancestry. So if you would prefer an identical starting state or a random starting state, whatever, we can redo the simulation with whatever starting state you want. But I'm telling you, the way I did it was the maximally charitable starting state for the separate ancestry position.
If it was maximally charitable and you said I can choose any starting state, I'm saying I want to choose the starting state that you chose.
But then you're choosing a shared common ancestry.
No, that's your assumption that that's common.
No, it's not. That's just how. Look, we have a level
it
of
is something you're imposing onto the data. I was going to say
we have a level of variation that exists in the present, and at creation we agree that you can only have in each created kind a small subset of that variation, right?
But you're comparing.
Hold on, but we have to know what the genes work, what their functions are, and everything from the start. We don't know every single thing that was supposed to be there from the start. That's what you're assuming.
Can I try
How many
this?
alleles can you get at the start? Tell me a number. How many alleles can you get at the start with a population of either 2 or 7, depending on the species, coming off the arc? What is the maximum number of alleles you can get? Tell me a number.
It depends on the actual.
It literally
yes, it does. It depends on the genomes that we had to start with.
No, it doesn't.
Yes, it does.
It depends on the number of things that get off the arc. That is it. If there are
but
7
how do you know what the starting is
for
those animals that got off the arc?
If you have 7 individuals of a kind that get off the arc, you have a maximum of 14 alleles, right? Yes or no?
Wait, if you have.
This is a question for Pigs Can Fly. If my understanding, I'm not a Bible scholar, my understanding of Genesis is that either, depending on whether they're clean or unclean or whatever, either 2 or 7 of each kind got off the ark, right?
Yeah, but you're assuming that the variability is not right. Hold on, stop, Mr. Dan. Please let me respond before you continue, because you're asking me a question and trying to respond to you.
I just need a number.
No, you don't. You need an actual response instead of something that's.
How many alleles can you have in 7 diploid individuals? How many distinct alleles can you have?
Yeah, you have the 14. However, we don't know what the maximum genome size looked like, how many children they had. We don't know anything about that stuff.
Doesn't matter.
You're assuming so much stuff with the way you're asking the question.
Okay, yeah, I agree with what you're saying, Dr. Dan. Okay, right. There's a certain number of alleles that they can have. And now, I mean, there might be.
And you can make them in whatever pattern you want, similar, different. Right. It doesn't matter, because the point is you only have this many, and you need to generate this many.
If it's 2 animals getting off the ark, then you have 4 possible alleles, right?
Possible alleles.
Okay. Now,
for many loci, you need to generate thousands.
Exactly. Now, we're on the same page with that. We're on the same.
Do we agree that the main way that's going to happen is mutation?
Okay, well, we're going to have recombinations.
But the recombination rate is 1 crossover per arm per chromosome, per meiosis. So we can calculate the mutation, the recombination rate. I've done that math. And it's, again, several orders of magnitude too slow to generate the variation.
Okay, but remember what you're starting with. So, but in the paper that we're discussing, it is not talking about getting the variation in one kind. It's comparing between human, chimp, and gorilla, which we say are separate. So we don't have a starting point. Now, if we were able to say, you know, what they were when they got off the flood, then we could calculate, you know, the differences or whatever. But it's the starting point is what we don't know. We don't know. We know the number of alleles that can come about by recombination. And I mean, generally we can calculate, and mutation. But
you
don't know for human, chimp, and gorilla is what they actually started with. How many similarities did they start with?
And what I'm trying to convey is that the model, the way they did their calculations is that the calculations converged on the maximally charitable starting point for each model.
But there's no maximally charitable starting point for our pattern, because we could, and this is what I'm going to say, there's not a scientific starting point.
We have the existing variation, right? We have A, we have the arrow, and we have B, right? And you're saying, well, what was A? And I'm saying they didn't tell you A. They didn't start with the defined A. We know B, we know the ending states, and we know what the arrow looks like. So they're saying, given those two things, what is, if we had the best possible A, what's the likelihood you get from separate A's to all the B's, right? They didn't define those A's. They just used a model that found the best ones.
Are you two trying to say that somehow these other alleles that were not at, like, you agree that there were 4 options for alleles at that location if there's only 2 animals? So are you saying that they had all the other alleles at different locations in the genome, and it's like somehow through some mechanism all those alleles migrated to the locations that they are currently in all the different ancestors? Are you trying to say genetics worked differently in the past?
No. Well,
I don't understand what you're saying.
What's going on here? What's going on here? Go ahead. But I do just, I wanted to answer Grayson's question about what we're doing with the separate ancestry thing and answer. I think we are conflating 2 different issues, because if we're talking about variation of alleles, like what we see starting with in alleles of the same kind, right? Then we can go back and kind of like say we know at the flood, basically if we're going with the flood model, then there's only a certain potential, right? But the critique that I'm making about the paper that compares the separate ancestry and common ancestry with regard to primates is that we're not starting with that same thing, because we don't need to get, we don't have to get to a certain variation. Okay.
You do that because you have to get to existing variation.
So but then am I misunderstanding? Because from what I'm understanding,
we all need to arrive at, to borrow a phrase, we all have our limitations, right? We all are constrained by what currently exists in the present that we've documented.
Right.
So no matter what your model of origins is, you have to arrive at the current level of biodiversity that we have documented.
Yes.
And we have a specific set of processes that we have very specifically documented to get us there. And we've talked about this, and you're not proposing like ongoing tinkering or vastly different processes operating 4,000 years ago compared to now.
No.
Right? So we know what the processes are to get us from A to B.
Right.
We know what B is. So what we're trying to do, if I understand your critique, is that we're not giving you the correct A, right? We're not giving you the right starting point that gets us to B given the processes. Is that fair?
Yeah, exactly. Like
B
is what we see now. B is what we see now.
B is what we see now.
And we're trying
to
get
giving you the right A, right? I'm not giving you the right A that allows your model to get us there. What I'm trying to convey is in the little simulation that we did together the other night, I'm giving you the best possible starting point for your position by building in the current pattern. And then in that paper, they do even better than me by saying, we're not going to pick a starting state. We're going to let the data tell us what starting state gets us the closest.
But how can you compare starting states if you're not assuming a starting state?
What I mean is data determine the best possible starting state.
Part of it too, if I'm understanding it correctly, is that like a lot of it depends on like how many steps it would need to take for like sequence A to transmutate into sequence B, right? Like you can have different things like that happen, like where, for instance, like A mutates to T, A to T, A to T, A to T, A to T, and eventually end with an A, right?
Right.
But you can also just have an event where something that was a T mutates into an A, right? And this, right? And the kind of thing that can happen, right, is both of these are like plausible, right? But it's very unlikely that you have this like single nucleotide, that's mutating every generation between A and T, right? God knows how many times, versus one single event of, like a T being mutated into an A,
parsimony, exactly.
So there are certain events like that when you're doing these computations, right? You can have the same ending sequence, right? But certain processes just probabilistically, given you know something about the rates at which they occur, like that they're observed to occur at, how likely is it that this process gave you the sequence that started with an A versus this one that started with an A? And the algorithm is taking charitably the one that has the highest likelihood.
Thank you. Yes, exactly. Thank you.
Okay, so and look, I'm not trying to give you guys a hard time unnecessarily, okay? Like I mean, I will just admit up front, I could be massively misunderstanding this, okay? So I am open to being shown what I'm missing, but I still don't feel like you guys are listening to me about the starting point.
State would you like?
Because what the question that I would like answered is if like I'm saying, look, I cannot know the starting point for human, chimp, gorilla. I can't know that starting point. I don't know which genes they had in common, even though they were created separately. They may share common genes, okay, because they're trying to get the common functions. So what I would like to choose, since I know Dr. Dan's starting point for that demonstration leads us to the where we are today, I'm saying, why can't I choose that as my starting point for separate ancestry?
You can, but that makes you an evolutionist.
Can I try this one?
It doesn't,
Rebecca. Dan's model does not start with 3 different genomes. His starting point is one genome that then mutates and evolves into 3 different ones. So that's the reason why you cannot use Dan's starting point, because his starting point is not 3 separate genomes, it's one genome. So if you used his starting point, that would be common ancestry.
Okay, now, okay, but it's not going all the way back, right? Like it's okay.
Yeah, okay, but it's not supposed to.
Okay, hold on. You guys might be having I might be having a breakthrough. Okay, you might have finally helped me understand. Okay, so just hang on. I'm not sure I can declare it right now, but let me think on it. Matt, do you have any objection to this? Are you following this argument? Because I know you may not have been part of all this. So
no, I mean, I still feel like there's a certain starting point they have to assume every single time. It doesn't really matter, and it's always arbitrary, even if they want to say it's not. Ultimately,
can I ask Pigs Can Fly a quick question? Is there any starting point that you feel like separate ancestry, like any possible combination of genes and alleles and whatever, any potential starting point that could result in our current diversity today?
You mean through common ancestry, you said?
No, through separate ancestry. Like you're saying that, oh, there's assumptions about the starting point. I'm saying, like, out of every single mathematically possible combination of nucleotides, is there any possible starting point that could result in today's diversity patterns?
I mean, if we have all of the different mechanisms that are actually categorized and taken into account, I think we can get a proper model. Yeah, but that's what I was mentioning before about the mutated genome decay. I don't think that was even taken into account to any of the things that we're talking about. And of course, Dr. Dennis, here we go again. We're going to keep. Listen, Dr. Dan, I've been sat here for literally over 20 minutes just listening to you. I'm sorry, sir, but I just have to. But it's
he addressed your point already.
I did address your point in the
he directly explained the mutated genome decay despite sustained fitness gains paper. He explained the survival of the flattest. Like, he did go through that explanation.
Address that.
Okay, so now you guys are saying Dr. Dan's starting point is complete equal genome, like one genome is the starting point. But what I remember is that we took 5 of 15, right? Like, and I know this is greatly oversimplified. And what I remember from this, you know, basically the, you know, the paper that I'm reading is it's, you know, we actually, are we really starting from a like completely the same genome?
They're not
Are you
starting from
saying that?
any genome in the paper. They don't pick a
Right.
starting state in the
Yeah,
paper.
Dan's simulation models has a starting point, but the paper itself does not
Paper does
assume
not have a
different starting
starting point.
points.
Okay, so
It doesn't have a fit. We should say it doesn't have a
right.
fixed starting point. If you dug into the models, if you ran their models, you would converge at an optimal starting point for each model.
Okay. Okay, so now let's go back to your demonstration. Why can't I have the 5 alleles, I mean, the 5 nucleotides
Right,
out
5
of
and 5
15,
and 5, like I did,
right? Yeah, and we're greatly oversimplifying. 15 is not going to be
because it's
accurate,
haploid and whatever. Yeah, right.
but why can't I have 5 that are the
Out
same
of 3 that I made.
instead of 3? Because I mean, basically, you know what I mean? Like you did the nested hierarchy and
Yeah, and then I compressed it and varied the rest, right?
right. But
why
why
can't
can't I have the same starting point as you? Because I don't see how that starting point is common design.
Because you have to generate the existing variation in each lineage through mutation. In the common ancestry model, some of that variation occurs not in humans or chimps or gorillas, but in the common ancestor of all 3. Some of that variation occurs in the common ancestor of humans and chimps, and some of that variation occurs independently in each lineage. In the common design model, the vast majority of that variation must occur independently in each lineage. So I was actually being generous doing 12 out of 15. That was, you know, what, 80%? That's actually generous given the amount of variation you need to generate in each lineage compared to the starting variation in each lineage.
But how do you know the starting variation in each lineage?
Because you're set by the number of things that exist at creation or get off the ark, whatever thing you want to use.
But how do you know how many things are set at creation in the ark? But we're going between 3 items, not one kind.
If you have, like, let's use humans, right? Let's use humans, right? So you've got Noah and his wife, and they're going to have Noah's 3 sons, right? So in Noah and Noah's wife, you have 2 individuals, which is 4 alleles. You can have 4 variants of each locus in the genome, right? We agree on that. And
right.
Then in the wives, you have an additional 6 between the 3 of them. We're assuming they're completely unrelated, right?
Yes.
So that means the human family getting off the ark has a maximum genetic diversity of 10 alleles for each locus in the genome.
Okay.
Right? Okay.
Yes.
For many parts of the genome, you need to have at present over 1,000 variants. So you need to get from 10 to 1,000. And that's not just for humans, that's for everything that gets off the ark. So how are we going to do that? It has to be via mutations that occur independently in each lineage. That's why out of that perfectly nested hierarchy, I said, okay, let's compress it. And then we're going to take 80% of it and mutate it.
Right. But remember, that is a separate argument, because in this paper and in the demonstration, we're not trying to get the variation within humans. We're trying to calculate the variation between chimps, gorillas.
But you can't do those 2 things independently. You can't generate, like, if we wanted to, we could just say we start with the nested hierarchy and it stays the same. Great. But then you're going to have no variation within each lineage, right?
But what I'm saying is, okay, let's do it. You've got 10 alleles for the humans, right? Is that what you said? 10 alleles.
It was 10. Yeah, it would have been 10 getting off the ark, right? Your maximum number of alleles is 10 for each. Yeah, for each.
And then for chimps, you've got 4.
4.
Okay. Yeah. For gorillas, you've got 4.
4. And you have to generate 1,000
now,
in each lineage.
How do you know which similarities? How do you know what the gorilla? You know it only has 4 alleles for whatever thing, right? But you don't know what it shares genetically with humans and chimps.
And my assumption was that that comparison, that pattern of similarity, was a perfect nested hierarchy. That was my assumption.
Okay. A perfect nested hierarchy, but
when they stepped off the ark. Perfect.
Because that makes it the most probable to reflect today's current diversity.
Maintain the nested hierarchy that we speak, yeah.
But the nested hierarchy is the evolutionary scenario, right? I mean,
but the nested hierarchy is what exists in the present. So we both have to get to that from our different starting points, right? That's the point.
Right. Yes. Okay. Yes. So you're saying point B is a perfect nested hierarchy.
No, it's not it's far from perfect, but it is a nested hierarchy. Yeah.
Okay. But again, like, why can't I choose your same starting point? How is that starting with all the same genomes?
When you say do you want 5 nucleotides shared by each lineage?
I want
like 5 that are the same across all 3.
The 5 that you did. I don't remember exactly what you did on your thing.
It doesn't matter.
I think you did 5
that were the same. Okay, but the point is, if we start that way, I mean, sure, we could start that way, but the point is, that was the end result for me, right? That was saying at the end of the process, because the beginning is a common ancestor that's necessarily the same, because it's one common ancestor. They start identical. So are you saying you want to start identical and have mutations accumulate? Because we could do that.
That would mean that Noah and his family had identical genomes with all the other animals.
Well, that's what I'm trying to figure out. Look, if you're right, then I'll grant the point.
Rebecca, I think I understand what you're saying. I think I understand what you're saying. Okay, let me try to see if I'm correct on I think it just clicked for me. So what I did is say for the common ancestry simulation, I said they all start the same. And then they share that history for some amount of time, right? But then 2 lineages diverge. So now they have a different history. And then 2 more lineages diverge. They have a different history. And so you're saying, why can't you start the same? Like I assumed they started, right? In mine, it would have been like, oh, geez, or whatever, right? Whatever it was, right? And then, but the difference is, and here's why we can totally do that. I would love to just pull up the random sequence generator and do that. But the result of that will be gibberish for the common design simulation. And the reason that's the case is because you still need to generate the variation. So that means you can start identical, but then you still need to generate all those variants over the course of their evolutionary history. And instead of sharing a subset of those variants as they mutate, they're all going to accumulate mutations independently.
Okay, but like the thing that I think the difference here, though, and you can tell me if I'm wrong, is that like I only have to get the variance to generate within the kind.
And make a nested hierarchy. And make a nested hierarchy. There's 2 constraints here: existing level of diversity and a nested hierarchical pattern. You have to get both things.
Okay, wait. Say it one more time for me. You
need to get the existing level of diversity.
Yes.
And you need to get the existing nested hierarchical pattern.
Okay.
Right? So you can generate the existing diversity. If you have an identical starting point, it's trivially easy to generate the existing diversity. But because each lineage again, not my assumption, your model, right? Your hypothesis, right?
Right.
Each lineage is doing its own thing. So those mutations are going to be uncorrelated with each other. You won't get a nested hierarchical pattern.
Well, let's look. Cool. Okay, guys, you know what? I do have to work tomorrow, so I'm going to have to, and I'm sure you guys do. Look, but Grayson wanted to show something. He has evidence that he wants to present. Grayson, do you think you can do it in like 5 minutes? Because otherwise,
I'll go.
Okay.
I'll go. Grayson, thank you for pinging me, or like just mentioning me earlier. And Pigs, thanks. Rebecca, thank you for having me on. It's always a pleasure
It's a good
chatting.
conversation.
Thank you,
Thank
guys.
All right.
I mean, I really don't want the
God bless you.
conversation to end because this is really good, but I'm going to tell you, I am going to think about what you're saying here. I will rewatch this. I will read the paper you sent me. I will like think about all of this. Okay. So I like that we have this conversation recorded because I can go back and try to understand what's going on. Okay. So thank you very much for patiently working with me and thinking through what I'm saying. So appreciate you guys.
All right.
Yeah. Thanks
Later,
for having
folks.
us on.
So that was my ongoing conversation with Rebecca from Bread of Life on the topic of nested hierarchies and common ancestry versus common design, and why the evidence is strongly in favor of common ancestry. By the time this video airs, I will have also done something on that 2016 paper, so I'm going to link that down below once that link is available, and you can check that out if you want a really deep dive into the methodology of that paper that we were talking about. As always, everybody, please remember to do the algorithm-friendly things, because it's all about the all-powerful algorithm and who it smiles upon. So please remember to hit the like button, leave a comment, subscribe, share this video. If you are not a channel member, please consider becoming a channel member, and you will have immediate access when I upload pre-recorded videos like this, instead of having to wait for the public release date. Thank you all for watching, and don't get fooled.